Okay, welcome back to the final session. So I want to introduce Yuval Alaluf, who is a PhD student in computer science at Tel Aviv University, under the supervision of Professor Daniel Hohen-Or. And well, his research centers around leveraging generative models to give users greater control and creative freedom when interacting with visual content. So thank you, Yuval, for, well, I know that you could not be here, but thank you for participating. And yeah.
All right, thank you very much. Yes, I'm a PhD student at Tel Aviv University. Unfortunately, I could not be here in person. They canceled my flight at the last moment, but I'm still very excited to be here today to talk to you guys about some of the works that we're doing at our lab. And what we're going to see in the next hour is some of the ways that we're trying to take some of the state-of-the-art generative models in the context of, say, visual content creation and go beyond their capabilities, give users more control over these models, and kind of give users more creative freedom over what these models have to offer. So in the past, say, 2 years, I like to say that we started to go into what I like to call the era of language-guided generation. Right? Everything that we do today, a lot of things that we do is kind of guided by language. Right? And if we take a look 2 years ago, this wasn't necessarily the case. And if we take a look at some recent state-of-the-art text-to-image generative models that you may have seen, Stable Diffusion, DALL-E 3, Midjourney, these models are able to create some pretty amazing visual content. Right? So I'll focus your attention on this middle image over here from DALL-E 3. And we can see we have this Pixar-style animation with a hedgehog and sunflowers. And DALL-E 3, sometime during its training, it probably saw what a Pixar style is, probably saw what a hedgehog is, some sunflowers, even saw some text. Right? But the ability of these models to take all of these different components and combine them together into a new composition is quite amazing. So when these first models came out, many people, including myself, we kind of told ourselves, all right, we can kind of pack our bags and go home. This field has been solved. But you kind of quickly realize it's the exact opposite, right? On one hand, these models open up so many new possibilities, so many new problems that we can solve now, which we'll see later today, some of these examples. But on the other hand, you also really quickly realize that these models are imperfect, and there's a lot more room to improve these models. So we'll see some examples of this also later today. So to go into our first problem that these models kind of made possible. So if I give, say, Stable Diffusion a simple prompt, a photo of a dog, it's very, very good at generating a realistic image. But what if I wanted to, say, generate an image of my dog, right? My specific dog. Or, go beyond this and say, imagine my dog lounging on a beach, swimming in the ocean, or wearing a life jacket. Right? How can we force these models to generate images of specific personalized concepts, right? And this is a task that's called personalization. And this is going to lead us into the first work that we're going to see today, a work called Textual Inversion, which we presented last year at ICLR. And the idea here is that we want to kind of go beyond what these models know and introduce new subjects that the model can later use to generate new images. So if we went about trying to solve this problem, the simplest approach that we could probably think of was, say, given a set of images depicting our concept, let's try to describe the concept in very specific detail, right? Give a very detailed prompt, and hopefully the model will be able to reconstruct it. And this is exactly what we did. We asked someone, how would you describe this object in a way that would allow an artist to recreate it? And this is the prompt that we got for this teapot, right? You can see that this teapot is colorful. It has some leaves. There's some, a cherry on this teapot. And this is the prompt that we got, right? It's a very specific teapot. This is the prompt that we got. And if we took this prompt and passed it to, at the time, the state-of-the-art models, which was DALL-E 2 and LDM, also what we'll see later today, this is what we got, right? These models are able to generate a colorful teapot. There's some leaves, there's fruits, but that's about where the similarity kind of ends, okay? So what we're going to do instead is we're going to teach the model a new word. We're going to teach the model that from now on, when you see this teapot, this specific teapot, let's call it S star. Okay, we're going to add a new word to our vocabulary, and we're going to say this concept is called S star. It's a new word. And then what we can do is we can ask the model to generate an image of an S star. Okay, after we taught the model this new concept, we can recreate it. And this is what we get if we do this. Okay? And we can see that it's not perfect, right? But I hope you will agree that it's kind of a step in the right direction. And what's nice is because we're using a new word, we can naturally compose it into new sentences, right? And imagine our teapot as a watering can in a manga drawing, or even place this teapot as a poster for the movie titled The Teapot, right? So this is the goal that we're trying to achieve here with textual inversion, with personalization. And how do we teach the model these new concepts? So before we get into using textual inversion, we have to talk about how these models work under the hood. And the models that we're going to see today is called latent diffusion models, okay, kind of the state-of-the-art open source models that are commonly used. And these models work in two steps. Okay? The first step is a kind of simple autoencoder that's going to try to encode an image into an intermediate latent space and then reconstruct the image from this intermediate representation using some sort of reconstruction loss. Now, there's some other technical details over here, but nothing that we have to worry ourselves with. The first step is this autoencoder. Because what we really care about is this latent space, this latent representation of the image, and hence we get the name latent diffusion models. So what we're going to do now is what's called a diffusion process. We're going to iteratively add noise to our latent, Gaussian noise, for t time steps, each time adding a bit of noise until we get a noise latent code that's called ZT. Right? T, in this case, is usually 1,000. Okay? Now, we have this latent representation, and then we're now tasked with trying to remove this noise. Okay? So how do we do this? This is called the denoising process, where we're given ZT, the current latent, and we're going to pass it into a UNet model, okay, that's given this the latent code ZT and the current time step T, and the model has to try to predict the noise that we added during the diffusion process at the current time step T. Okay, and this is a model that we're going to train, okay, and we predicted the noise. We're going to remove this noise to get ZT minus 1, and then we're going to repeat this process. We're going to pass ZT minus 1 to the same UNet each time, trying to predict the noise that we added at the corresponding iteration, okay, at the corresponding time step. Then eventually, after T denoising time steps, we're going to get back to Z0 and pass the latent to the decoder and reconstruct our image. Right? So this is the general process of a diffusion process and a denoising process. And where does text come into play over here? So say here we have a text prompt that's going to describe our image, in this case, a photo of a corgi. We're going to encode it into, say, a representation using a text encoder, for example, clip. And then we're going to pass this representation into the UNet layers. And this is a process that's called cross-attention, which we're going to see later on. This is pretty much going to guide the UNet, guide this denoising network, into removing the correct amount of noise at each time step. It's going to tell it, hey, I want to generate an image of a corgi. So once I've trained this model, I've trained this UNet, in order to generate new images, what I can do is I can simply sample different initial noise latent codes from a Gaussian distribution. And then each new set of initial noise, I'll get a different image of a corgi. Right, so this is the general idea of how we're able to generate images with these text-to-image models. But the question is, what do we really care about when we're talking about personalization? What we really want to do is, given a small set of images, we want to encode these images into a new word, S star, in the input space of the text encoder. Right? And this new word is going to guide this denoising process that we saw. So let's dive in a bit deeper and see how language models typically work with these text-to-image models. So most of the models today, they start off with some embedding step. So we're going to take each word or each subword, called a token, and map it into some predefined index. And then we're going to map this index into a vector that's going to represent an embedding that's going to represent this token, right? And these embeddings were learned when we trained this language model. Now, what we're going to do is we're going to take this S star and map it into a new vector V star that we're going to learn, right? Everything else is going to remain fixed, and we're only going to train this V star in order to make it represent our personalized concept. Okay, so let's assume that we have this V star. We'll see in just a second how we're going to train this. But say we have this V star. We're going to pass all of these vectors into the text transformer, okay, into the architecture itself, and it's going to pass us. It's going to give us this conditioning vector that, using this cross attention that we saw earlier, we're going to pass this into the UNet to guide the denoising process. Right, so this is a high-level overview of where this vector is going to come into play. But how do we train this vector? So we're going to start off with a small set of images, say 5 images, even sometimes you can work with a single image of your concept. And at each optimization step, this is going to be an optimization problem. At each optimization step, we're going to sample an image. We're going to sample some intermediate time step of the denoising process and add some noise. Okay, epsilon here is the Gaussian noise that we're going to add. And then we're going to pass this noised representation into the UNet. That's going to be tasked, like we saw before, it's going to be tasked with predicting the noise that I added. And in order to guide this prediction, we're going to inject this text representation of a photo of an S star into the UNet. This is going to tell us, remove this noise such that I'll be able to reconstruct my image of an S star, reconstruct my image of the teapot. So I'm going to get this denoised image, and I'm going to compare it with how much noise did I add to how much noise did my model predict, right? And using this noise, what we're going to do, using this prediction, right, we're going to backpropagate the results and update that V star that we saw earlier. Right? Everything else is going to remain fixed. This UNet is going to remain fixed. The text encoder itself is going to remain fixed. And we're only going to train that single vector V star that's going to optimize that representation of our concept, right? So at the end of this training, hopefully V star is going to represent my teapot. Right? Great. So that's the main idea. That's the general idea of how textual inversion is trained. So let's see some of the results that we're able to achieve with textual inversion. And the first question that we really have to ask ourselves is whether this process is able to actually capture the concept itself. If I give it a prompt, a photo of an S star, is it really able to reconstruct my concept? So there's these. Let's look at 2 examples. On the right, we have this teapot that we saw earlier, and on the left, we have this kind of mug with skulls on the bottom. And the results that we get with textual inversion, we can see them on the bottom row. We can see that we're able to nicely reconstruct the image itself. And in this middle row, we have a method that's called DALL-E 2 images. And what we did here is we took the images, encoded each image using clip, okay, to extract an image embedding of this image, and then we pass this representation directly to the UNet, right? So we're kind of, in a sense, going directly from the image into the UNet. And we can see that if we do this direct approach, we're not able to reconstruct the objects. But say that we were able to perfectly reconstruct the objects, this isn't very interesting because we would only be able to recreate the object itself. We wouldn't be able to place the object into new prompts. Right? But because with textual inversion, because we're learning a new word, we're expanding our vocabulary, we can use this word, we can use this language, right, and place it into new prompts. So this is exactly what we can see over here, where we have these 2 examples. In the first row, we have this kind of bird that is made out of rock. So we can place this bird, make it out of a watercolor painting. We can make a house that is in the style of this bird, or make this bird made out of chocolate. Or in this bottom row, we have this bowl, right? And I think this is a very nice example because the model, the textual inversion, was able to understand that this is a bowl, right? It was able to nicely capture the semantics of the object and knows that, okay, wait, this is a bowl. I know that I can place objects inside of this. Right? So we're able to place a mouse in this bowl or put soup in this bowl. Right? So we're able to nicely capture the semantics, which I think is pretty cool. So when we tried to compare textual inversion to several different baselines, but nothing really came close. Right? It's kind of at the time, it was kind of a new task. But I do want to focus on one key idea here, and this is a comparison to Palavra. Now, Palavra, their solution, what they're trying to do is, given a specific object, okay, we have this image of a specific object, and we have a database full of images. I want to retrieve images of this object from my database. But that's the main problem that we're trying to solve. In a sense, it's kind of similar to what we're trying to do with textual inversion. And the solution approaches are quite similar as well. What they're going to do as well is, given this image of my object, we're going to learn a new word that represents our object, such that it will allow us to retrieve it using a text-based search, using clip, for example. Right, so they're also going to learn a new word, just like we're doing with textual inversion, but they're going to try to do it for a retrieval task. And it raises the question of why these two results are so different. And here I can only kind of speculate, but I think it has to do something with the fact that with Palavra, they're trying to solve a discriminative task. Right? They're trying to solve a retrieval task. And when you try to solve a discriminative task, it may be enough to simply get an approximate solution. Right? I don't need to perfectly encode my object using this representation. I just have to get a good enough approximation. Right? If I want to retrieve an image of a mug, then I just need to understand, say, maybe its color and the fact that it has text on it. The exact text and the style of the mug is maybe a bit less important. I don't care about that fine level detail. When we're talking about textual inversion, we're trying to solve a generative task. Right? And in order to solve a generative task, I have to have a very, very accurate representation of my concept. Right? Because if I don't have an accurate representation, I'll generate an image of a mug. It'll maybe look like my mug, but it's not my specific mug. Right? So because we're trying to solve a more difficult task, right, we're able to solve, what we need those fine level details, we're able to get a much richer, much more expressive representation. I think that's what brings the difference between Palavra, this discriminative approach, and textual inversion, this generative approach. So when we first published textual inversion, the state-of-the-art model was LD, it's called the LDM, latent diffusion models, and very soon after, Stable Diffusion came out. And Stable Diffusion has since then become the go-to generative model, the open source model. So we said we have to try textual inversion on Stable Diffusion. So if we do this, let's see what happens. When we try to take this statue of a cat with colorful stripes and try to encode it using one token, like we did earlier, we can see that we're not really able to reconstruct the object. So we told ourselves, okay, let's try to help the model out. Let's try to give it some more capacity. And instead of encoding into one token, let's try to encode it into 5 tokens. Or in other words, encode it into 5 new words in my vocabulary. And if we do this, we're able to kind of nicely reconstruct my cat. Right? We get its shape, its tail, its colorful stripes. But then the next thing that we have to ask ourselves is, okay, we were able to reconstruct it. Can we now place this object into new scenes? So if I give the model the prompt, a photo of a S star on the beach, we see that we're not able to do this. And it turns out that what happened was we not only overfitted the representation, the object, we also overfitted to the background that was in our training images. So this is not very good, and we have to understand, the first thing we have to try to figure out is why is there such a big difference between LDM and Stable Diffusion. So the main difference between these two models is the text encoder that they use. LDM uses a BERT model that was trained during the training of the denoising network, during the training of the UNet model. Right? So BERT was trained for a generative task, and they went from BERT into a pre-trained CLIP model. So here we're again faced with this discriminative versus generative task. Right? BERT was trained on a generative task because we fine-tune it. We fine-tuned it while we trained the diffusion model. While a pre-trained CLIP model was trained on a discriminative task. It was trained on a contrastive loss between a set of images and a set of text. Right? So perhaps CLIP simply doesn't care about the finer level details and is good enough with an approximation. Right? So we fail to capture the fine level details that we need for a generative task. And the second maybe explanation for this is the fact that we simply have a much smaller model. We went from an 800 million parameter model to a 100 million parameter model, and the embedding itself is about half the size. So perhaps CLIP is simply a less expressive model. It perhaps has less capacity to learn this task. But in either case, we have to try to figure out how to solve textual inversion with diffusion. And I'm going to jump right into the solution. We found that in order to solve textual inversion with stable diffusion, we had to allow the model, kind of had to fine-tune the model itself. We allowed the model to slightly change its weights during the training of the vector v star. And by doing this, we were able to also capture and reconstruct the object. But because we only slightly changed the weights, we didn't disrupt completely the prior that the model had already learned. Right, so let's see some results that we have here. Here's the cat statue that we just saw. So we're able to nicely capture the general semantics of the objects and place them into new prompts. Now, there is a problem with the approach of fine-tuning. These generative models themselves, they weigh about 3 gigabytes, right, each. So if I have to fine-tune the model for each concept, this is going to be very, very expensive, right, in terms of storage. So we're kind of left here with these two endpoints, right? Because on one end of the spectrum, we have textual inversion, which is a very lightweight approach, only going to optimize for a single vector, but it may not be powerful enough to capture complex objects, especially with stable diffusion. On the other end of the spectrum, we have these fine-tuning approaches where we have these very large models that we have to store, but because we're fine-tuning them, we have more capacity. And we're able to nicely capture the objects, but we also may be prone to a bit of overfitting, right? Because if we don't do this correctly, we're going to forget the prior that the model has learned. So we have these two endpoints. And in the next work that we're going to see, we're going to try to kind of find a middle between these two ends of the spectrums and find an approach that gives us the quality that we see with fine-tuning without changing the model weights themselves, right? So we're going to reduce the storage costs a lot. So this work is called NETI, Neural Textual Inversion. We presented it just last month at SIGGRAPH Asia. Excuse me. And the idea here is we're going to try to train a small model, okay, that is going to give us a lot of capacity in order to encode complex objects, but we're not going to try to touch the model itself. We're not going to change the generative model itself. So we just saw textual inversion, right, where this idea of training a small model is great because it's very lightweight, but we have a slow convergence. There's a very long optimization process. Typically takes about a couple hours on a simple GPU, and it's not very good at complex objects. Now we just talked about fine-tuning approaches, right, where this is great because it gives us good reconstructions, but it has the storage overhead. So with neural textual inversion, what we're going to do is we actually introduce two different changes to what we just saw. We're going to first consider a new latent space, this text conditioning latent space, that is going to consider both the denoising time step and the architecture of the unit itself. Right? So we're going to consider both what's called space and time. And we're going to introduce a new neural representation of our concept. Well, you'll see exactly what I mean by this in just a minute. So let's start off by talking about this text conditioning space. So with textual inversion, we learned a single vector for all the different denoising time steps, right? For all the time steps during the denoising process and all the layers of the unit model, all the layers of the denoising net. So the space is, let's call it the P space. We have a single vector for all these possible inputs. A bit before we published NETI, researchers from Google, they said, okay, let's kind of leverage the architecture of the unit, and let's train a different vector for each layer of the unit. And there's 16 different layers, so we are going to optimize 16 different vectors for each of the layers, but we're going to share these vectors across the different time steps. But we naturally asked ourselves, why stop there? Why not combine both space and time? Why not also use the fact that we have this denoising, this iterative denoising process? So this is what we did with our P star space, that we simply tried to learn a vector for each different layer and for each denoising time step. But if we do this, if we think about this for a second, we have 16 unit layers, and we have 1,000 denoising time steps. Right? We have 16,000 vectors that we have to optimize, and this can be quite challenging to do. So we're going to need a slightly different approach. And the solution that we found was, let's use a neural representation. Okay, so what I mean by this is, let's train a small mapper, a small mapping network. It just weighs about 2 megabytes in size. It's very, very lightweight. That's going to receive the current time step and the current denoising layer, the unit layer. And this is going to output the current representation of our concept at that time step and at that layer. So we're still going to learn a different embedding for each one of each combination of layer and time step. We do this with a model that is shared across all possible inputs, right? In a sort of implicit fashion. So this model is going to give us a nice balance between the representation that we're going to train, and we get a more capacity to capture these complex objects, but don't have to touch the unit model itself. So how does training work with neural textual inversion? It's going to be quite similar to what we saw before. We're going to say, take a prompt, a photo of an S star. All the standard tokens are going to map into their embeddings that were predefined. And for S star, rather than directly mapping it into a single vector, we're going to kind of disentangle it into different inputs. For each combination of time step and layer, we're going to output its token representation at the current time step and the current layer. We're going to pass these embeddings to the text encoder, which is going to give us this conditioning vector that's going to be passed into the unit. And here we're going to pass it only to that specific unit layer. And this process is going to be repeated for all the different combinations of time step and layers. But because, even though we're repeating this for a lot of different inputs, because the model itself is very light, this is going to be very, very efficient to do at inputs. So for training, we're going to use the same optimization that we saw before. At each time step, right, we're going to try to predict the amount of noise that we added. And based on this difference between the amount of noise that we added and the amount of noise that we predicted, we're going to update the weights of the model. Right? So just like we updated the weights of V star, now we're just simply going to update the weights of the model themselves. And in a sense, what we're doing here, I think it's kind of cool, is we can think about the concept being represented by the network weights themselves. We're kind of encoding the concept in an implicit manner inside the weights, kind of like how nerfs work, right? We're going to completely capture the concept in the weights of the network, and then we can simply query it for all different possible inputs in order to reconstruct my concept. So that's the idea of this neural representation. So let's jump right into some results that we're able to get with NETI. So we can take this skull mug that we saw earlier and make it into an espresso cup or a wine bottle or into say a pitcher of beer. We can take this cat and make it wear sunglasses in a hammock, put a chef's hat on, read a book, and things like that. And we get some really nice quality results using NETI. Now, for some quick comparisons with the other portions that we saw. So with textual inversion, even if we're trying to train this for 5,000 steps, we saw that it simply does not have the capacity to capture these objects, right? With a single vector, we're not really able to learn all the fine details that we need. And if we train the other three methods for the same number of time steps, right, each one is the optimization problem, but in a slightly different way, then NETI is able to really nicely capture both the structure of the cat and its stripes and place them as a graffiti on the wall. Right, so the other methods, they do fall short in doing this, while NETI is able to succeed. And similarly to the example that we see on here on the bottom, we're able to preserve the yellow hat of the boy and its kind of string-like legs and place this boy in Times Square. Right, so in a very realistic manner. So that's pretty nice example. Now, we want to ask ourselves, a natural question is, do we really learn different aspects of the concept at different time steps? Where we kind of added this idea of of time into this process. Does this really help us? And the question is, the answer is yes. We actually are able to learn different aspects of the concept at different time steps. And we found that typically, at the earlier denoising time steps, we're able to capture more general shape, structure, and general color. While in the later time steps, we're able to focus mainly on the finer level details, such as color and texture that we see here on the right. Great. So we talked about personalization, this idea of teaching the model these new specific concepts and subjects. But until now, we kind of assumed, more or less, that any prompt that I give the model, we're able to get an image that accurately depicts this prompt. But this is not always the case, as we're going to see in the next work. And this is a work that's called Attend and Excite, a paper that we presented at CGRAPH last summer. And to motivate this work, let's go back to this idea of a photo of a dog and a photo of a cat. And if I give, say, Stable Diffusion, these two prompts individually, we're able to generate very nice images of both a cat and a dog. But now what I'm going to do is I'm going to try to make this just slightly harder and ask Stable Diffusion for both a cat and a dog, right? And if we do this, we get this kind of very strange looking result that kind of tries to merge these two dogs together into one hybrid dog. And this is not exactly what we want. The question is, why does this happen? And to try to understand why this happens, I want to try to answer three different questions. The first question is going to be, where do these models fail? Where do these models fall short? We can then try to dive in and try to understand why these models fail. And finally, we can try to understand and formulate a solution into fixing these issues. So let's start off with where. Where do these models fail? And in this work, we focused on two semantic issues of the model. There are many other issues. We're only going to discuss these two that we're going to see here. And in the first example, we have a prompt, say yellow bowl and a blue cat. And we can see that we're not able to generate a cat in the image. This idea is going to be called catastrophic neglect, where one or more of the subjects is not going to be generated by the model. In the next example on the right, we have a prompt, a yellow bow and a brown bench. And we can see that kind of the yellow of the bow leaks onto the bench. And we're not able to accurately color the bench brown. This idea is going to be called incorrect attribute binding, where we're not able to accurately match the attributes, in this case color, to their correct subjects. So we're going to try to tackle these two issues with our Attend and Excite approach. But the question is why? Why do these models fail at addressing issues? So let's go back to the standard denoising process, right? We start at each time step. We have this intermediate representation, this T. We're going to pass it into the denoising network, into the denoising unit, to try to remove this noise and do this iteratively. And to guide this process, we have a prompt, a lion with a crown in this case. And this prompt is going to guide this unit into removing the noise in the direction that will give us the desired image. And if we do this, we're going to get a lion, but with no crown. So what I want to focus on now is this interaction, right, that we see here between the unit itself and this text embedding, right? This injection of the text embedding into the unit model. And this injection, as I mentioned earlier, is called cross-attention. So how does cross-attention work at a very high level? We're going to take a look at a specific intermediate layer of the UNet. Okay, we're going to just flat out its feature map into a vector. Then we're going to take this text embedding, and that's going to be of length n, where n is the number of tokens that we have in the prompt. And we're simply going to multiply these two vectors together. It's going to give us an attention matrix AT at the current time step t. And what's cool about this matrix is that we can actually look at each column of this matrix as representing each one of our tokens. So I can actually take each column and reshape them back into an image. And what we see here, what we can see here is with these images, each image is going to tell us each token n. Okay, for each one of my tokens, say a lion, say crown, how much information is going to be passed from token n into each one of the image patches ij. Right? So in other words, where is token n going to appear in the image? Where is the lion going to appear in the image? And where's the crown going to appear in the image? Right? How much information am I going to pass from each token to each one of my image patches? So why is this the source of the issue? So if we think about this, nothing is explicitly encouraging all the subjects to be generated by the model. Right? The model, nothing is encouraging the model to consider all of the subjects. Right? Nothing is telling the model, wait, make sure that each subject appears somewhere. Right? So intuitively, our idea is to verify that all subjects have a strong activation somewhere in the attention map. Right? And if we have a strong attention somewhere, perhaps this will help encourage the generation of each one of our subjects. So how do we do this? How can we quantify how strong of an activation each token has? So what we're going to do is we're going to only look at the nouns or the subjects of our prompt, in this case lion and crown. We're going to start off with a Gaussian smoothing over the attention map, just to kind of smooth things out. And what we want to do is we want to compute the maximum activation that we have in each one of these attention maps. Right? And ideally, what we want is this maximum value to be as high as possible. So using this idea, we can define a loss that says how close are we to having the highest possible activation. The highest possible activation is going to be 1. Right? So if we have a high activation somewhere in my attention map, this loss is going to be low, and vice versa. So we're going to take these two losses for each one of our subjects and simply take the maximum of the two. And what we're trying to say here is that we want to consider the most neglected token that has the lowest activation. And we're going to try to strengthen this most neglected token. Because if the most neglected token has a strong activation, then it must be that all the other tokens have a strong activation as well. So we're always going to try to consider the worst case. So we have this loss, and now we have to define an update that will guide the latent to the desired solution. And what we're going to do is perform a gradient descent over the latent, right? Kind of in a similar fashion to what we do with classifier guidance, for those of you who are familiar, where in this case, the loss that we have is going to be that loss that we just defined. So the idea here is that at each denoising time step, we're going to slightly push the latent in the direction that will minimize the current loss. Right? In other words, strengthen the activation for all of our tokens. So this is the update rule. Let's try to put all of this together and see how this works at inference time. Right? There's no training going on. This is simply going to be applied during the generation process. So at the current time step, each time step, we have ZT. We're going to update it into ZT tag, pass it into our UNet to get ZT minus 1, update ZT minus 1 to ZT minus 1 tag, and then continue this process iteratively. Each time, updating that representation using our update rule, and then continuing to the next time step. Right? In each step, we're going to slightly guide this process, this latent, into the desired solution. And if we do this, then we're going to eventually get an image, now a lion, is wearing a crown. And the question that we can ask ourselves is whether we can try to improve this idea a bit further. And the answer is going to be yes. Right? And we can do this with something that's called iterative refinement. Now, it turns out that Stable Diffusion determines rather early on during its generation process whether, where, and even whether an object is going to be present in the image. So our idea is at certain time steps, say time step 0, 10, 8, we're going to keep updating our latent until a certain threshold, a certain activation is going to be reached for all of our subjects. So say we're at time step t, we're going to update zt, we're going to compute the loss on our updated latent zt tag, and we're going to ask ourselves, is this loss low enough? If it is, great, I'll continue. And if it's not, we're going to continually update zt until we get high enough activations. And then we're going to go on to the next time step. And this encourages each of the subjects to be generated early on, right? And we're going to be able to get images that better reflect the text prompt that we give it. So let's look at some results that we achieved with an Excite. And we're going to start off with a playful kitten that's chasing a butterfly in a wildflower meadow. And we can see that with Stable Diffusion, it's able to generate the cat in the meadow, but it's not able to generate the butterfly. As with the 10xi, we're able to generate all the three different components, and it also appears that the cat is chasing the butterfly, which is quite neat. And sticking with our cat theme, we have now this orange cat, fireplace, and this book. And Stable Diffusion does not generate the book, and oftentimes fails to generate the fireplace. Whereas with the 10xi, we're able to generate all three components together. And for a quick comparison, we did compare 10xi to two other baselines that also tried to mitigate similar semantic issues. But we can see that with Stable Diffusion, for example, it really likes to generate two images of cats. Doesn't really like to generate images of dogs. And the other methods, they either kind of form a hybrid of the subjects, or they fail to really improve upon the baseline of Stable Diffusion. But with the 10xi, we're able to nicely capture both the cat and the dog in the image. And going on to a slightly more complex prompt, here we have a red bench and a yellow clock. And we're able, with the 10xi, to consistently generate both the red bench and the yellow clock. Whereas the other methods, they either fail to generate both the subjects or will mix their attributes, making the bench yellow or making the clock red. So we talked about this idea of personalization. We talked about how we can improve the fidelity of these models using what I call semantic guidance. We're going to guide the latent into a desired solution using a sort of simple loss that we can define. What I want to do in the final work that we're going to see is ask ourselves whether we go kind of beyond personalization. So what I mean by this is, let's say I don't want to just generate images of a specific object. Are we able to kind of teach the models how to generate concepts that they've never seen before, right? Generate kind of imaginary ideas, right? And we'll see exactly what I mean by this. This is what we try to tackle with this idea of creative generation, right? Kind of unlocking a new layer of creativity with these generative models, right? This is the work that we published called Concept Lab. And what we started today talking about this idea of generation, right? Where I want to generate a pet, let's say, and put this pet on the beach, or make a children's book about a pet. We then talked about personalization, where we're going to learn a new concept, a new personalized specific concept of my pet. And I want to place my pet on the beach, or make a children's book about my pet. With creative generation, this new task that we want to try to solve, I want to try to generate a new pet. I want to generate a pet that does not exist, okay, that the model has never seen before. And I want to place this new pet on the beach and make a children's book about this new pet. Or say I want to do this for fruit. I want to generate a new fruit. How can I imagine a new fruit as a juice bottle? right? And this is the idea of creative generation. How can we take these generative models and teach them concepts that they have never seen before, right? And use them as language into new prompts. Right? So what do we want to do here? And I'm going to stick with this idea of pets, right? Let's say I want to generate a new pet. So we have a space of all possible pets in the world. And this is my representation of my concept. Kind of similar to the representation that we saw with textual inversion, right? I have this single vector that's going to represent my concept. And this vector is going to be somewhere in the space of possible pets. But in the space of pets, we have this area that's defined by dogs. Right? So I don't want to be here. Let's move over here. I fall into the area of cats. And I have this area of hamsters, parrots. And eventually, I'm going to try to find this area, this missing area over here. And if I fall somewhere over here, I'll generate this image that we see here on the right. I can kind of do this for different representations, each time falling in a different area. And I get these different images. Now, all of these images over here, they kind of resemble a pet, right? They're very pretty and very cute looking, but they're kind of unlike any pet that we have seen before, right? The model has never seen something like this before, but it's kind of, it does resemble a pet, right? But it's just something that we've never seen before. So how do we do this? How can we learn these creative concepts the model has never seen? And if we think about this, we kind of have these two constraints. On one end, I want to be as close as possible to the representation of pets. On the other hand, I want my representation concept to be as far away as possible from the representation of dogs, of cats, of parrots, and so on. Right, so I have these two constraints. And how can I represent each of these constraints? So for my concept, we can think about this as kind of what we saw today. I can take my concept, place it into a prompt, a photo of a star, generate its, extract its clip embedding, pass it to Stable Diffusion, and generate an image. Great. And for my textual creations, we can kind of do a similar thing. We can take a photo of a pet, a photo of a dog, a photo of a parrot, extract their representation using clip, and then simply compute the losses between their text embedding and the image embedding of my concept. Right? And what we can do is train this V star, this vector that's going to represent my concept, using sets of losses. At each step, I'm going to pass it a prompt, in this case, a painting of a star, a painting of a pet, a painting of a dog, and so on. Say a star in the style of a cartoon. And at each optimization step, I'll generate an image, extract its embedding, and then compute the loss between this embedding and the textual constraints. And if we think about this at a high level, this does make sense. But in practice, there is one big problem here. Because for each optimization step, I have to generate an image. And this requires to perform a full denoising of the image. Right? So I had to do 100 denoising steps in order to generate an image. This does take about 10 seconds. Right? So to perform one optimization step in 10 seconds is very impractical. Right? It will never converge. It's very unstable. So we're going to need a slightly different approach to solving and to optimizing this representation. And until now, all the models that we kind of talked about, they kind of go directly from a text representation, text embedding, to an image, like we see here. Right? We have a prompt, extract its clip embedding, and pass it into the denoising unit. But now I want to talk about a kind of less well-known idea that was introduced in the original DALL-E 2 paper. This is the idea of a diffusion prior, or a diffusion mapping. And what we're going to do with a diffusion mapping is split this process into two. We're going to take this text embedding and kind of map it into an image embedding. And this image embedding is going to be more specific. Okay, so say I have a prompt, a photo of a hamster. This image embedding is going to represent a specific instance of the hamster, or say a specific breed of a hamster. And then we're going to take this image embedding and pass this into the unit model. Right, so this image embedding is, in a sense, going to represent my image. So what we can do is we really only need this image representation in order to compute our constraints, right? So I can take this image representation and kind of bypass this idea of generating an image, simply pass this text representation to the diffusion mapping, and compute this loss on the output space of the diffusion mapping, right? Because this is going to represent a specific instance of my concept. And then here, this is very efficient to do, right? I don't need to perform a complete denoising process. I can do this for any denoising step, compute my loss, and then backpropagate the results and update my vector. Right, so this defines the set of constraints. Until now, we kind of assume that we know all possible pets that exist in the world, right? We assume that I have this very large set of all negatives that I want to back away from. But this is kind of impractical to do. The question is, can we do this in a more adaptive or automatic setting? And what we're going to do is, at various intervals during training, say every 200, every 500 steps, I'm going to generate an image that's going to represent my concept. I'm actually going to perform this full denoising process and generate an image that represents my currently learned concept. Then what I'm going to do is I'm going to take this image and pass it into a vision language model, in this case blip2. And I'm going to ask the model what pet is in this photo. In this case, blip is going to say, here there's a hamster in this image. And I'm going to add hamster as a constraint into the next interval. Right? And what's going to happen is in the next interval of training, my concept is going to try to move away from hamster. So over time, as I expand this set of negatives, of idea that's called adaptive negatives, I'm adaptively adding more negatives based on my current representation. Over time, I'm going to get a representation that's more and more unique. Right? So let's see this idea in this idea of an adversarial vision language model. Right? We're going to start off the process with, say, a dog, and a cat. We'll get to a parrot. We'll get to a frog. We'll get to a rat. And eventually, after enough training, I'm going to get this image that we see here on the right, where it's going to be a pet, very furry, fluffy pet, but it's going to be very, very different to what exists today. And this process is guided solely by blip. Right? We don't need to define anything other than the fact that we want pets. So let's see some results that we're able to get with Concept Lab. And as I just mentioned, we only need to define the general category that we want to generate, right? So it's pet, a reptile, plant, superhero. We just need to define this general category, and we allow blip and these textual constraints to guide the process. And if we change the initial seed, we're going to add negatives, perhaps in a different order, and then we're able to get variations of the same concept. Generate different unique creations, right? So whether it's a fruit or a large map. And because during this entire process, we're still using language, right? We're encoding the concept into a new word, we can naturally place them to new prompts and imagine our concepts into new settings. Whether it's a superhero on a cereal box or flying in the sky, right? We can naturally compose these concepts into new settings. And this idea also works not just for objects, but for art in general. So using the same idea that we just saw, we can define sort of different prompts to use during training and discover new artistic styles. We have each row is going to represent a different artistic style that we discovered with Concept Lab, and we have 3 different prompts for each of the styles. Right, so all these styles, again, were automatically discovered using this idea of adaptive negatives. And finally, we talked about this until now. We said we have a single positive constraint and we have a large set of negative constraints. But we can kind of play around with this and say, forget about the negative constraints. I want multiple positive constraints. And if I do this, I'll maybe be able to get a hybrid of some objects. right? Say I can generate an image of a lobster turtle or something that kind of merges a snake, a hippo, and a zebra. And if we try to just do this with text naively, we're not really able to do this, right? But because we're able to learn how to get a representation that's close to both a pineapple and a watermelon, we're able to kind of merge them into a single concept. So to summarize, what are the things that you guys take away from this talk, right? So we started with personalization, this idea of teaching a generative model these new concepts, these new subjects, right? And how we can take this and place the subjects into new scenes. And we can do this using language, right? We're going to encode the model into a new word and then place this word into new prompts. We talked about this idea of inversion and fine-tuning, where each one has their pros and cons, right? But we're trying to balance this with the second work that we saw, which was NETI, where we also played around with this conditioning space and tried to use this idea of both time and space in order to get a stronger model that is able to nicely capture concept without fine-tuning. And we talked briefly about this idea of discriminative versus generative tasks. And again, this is just a speculation, but right, generative tasks, because you're trying to solve a very difficult problem that requires findable details, perhaps we're able to get a richer representation of our concepts. We then talked about academic sites, and we talked about this idea of semantic guidance. We're trying to guide the latent during the denoising process with no training. And in this approach, we use this idea in order to improve the fidelity of the model, right? In terms of the ability of us to generate multiple concepts or multiple subjects per prompt. But you can kind of use this idea and generate different losses, kind of define different losses based on the task you want to solve. There have been numerous very nice works that have said, let's define a loss, for example, that will move object within an image or change the object's color or make the object bigger. Right? So if I define my loss, I can guide these losses, guide the latent based on this loss in the denoising process. Right? So there have been a lot of works that have gone into using this idea of guidance. A lot of works have also tried to improve upon the work that we did with the Tandem site. There have been some very nice improvements for the ability of us to improve the fidelity of these generative text-to-image models. And finally, we talked about this idea, this new task called creative generation, where you want to generate concepts that the model has never seen before. That's unlike any existing pet or any existing fruit. We talked about this idea of defining sort of positive and negative constraints in order to drive this creativity and balance between being something I know, being something I don't want to be, right? And talked about this less well-known idea of a diffusion prior, which worked nicely in the constraint space. And what's nice here is that actually the diffusion prior was originally designed for encouraging diversity, but we're able to take this idea and create an effective space for our constraints. I think the big takeaway here, finally, the big takeaway is this idea of leveraging vision language models for driving the generative process. These models are very, very powerful, right? And the ability of us to kind of merge their knowledge with the knowledge of the generative models opens a lot of new potential. So I really hope to see a lot more works going into this direction as well. And with that, I want to thank you all for listening. If you want to read more about the works that we saw here today, here are the links. And if we have time for questions, I'll be happy to answer any questions. And feel free to reach out after as well. Thank you.
Okay, thank you, Yuval, for the presentation. Very nice work. So, there is any question of the audience? No? Oh, okay. Oh, okay.
Yes, thank you for that very creative presentation. There is quite some ideas for building movies for children, books for children, or who knows what, or even movies for adults that you can create. here. I just, yes, it was a very nice presentation. I just had maybe a question for clarification a little bit. I'm quite interested in this attend and excite model. And I think at some point you said that you strengthen the most neglected token activation, so at each time step. And I was wondering, do you consider all tokens? It seems that you consider objects, nouns, or do you consider also other tokens like adjectives or?
Yeah, so we only consider the nouns in the prompts, and there's this trade-off, right? Because you could try to maybe consider also strengthening the attributes, and maybe also get a stronger, say you want to strengthen the color of an object, you may be able to do this if you strengthen the color. We focus on only the subjects, and we saw that if you only strengthen the subjects, then you also are able to strengthen the attributes as well. Right? We kind of only focused on solving the problem of neglect, but by solving the problem of neglect, we're also able to handle the issue of the attribute binding without explicitly addressing the problem of the attribute binding. One limitation of our approach, I will say, is that, for example, if you have relations between objects, that you want to have an object that is chasing a different object or one object on top of the other object, that's something that we weren't able to solve, right? So there's still more work to be done. I think there have been works that try to solve these limitations, but I will say this is still an open problem, and I think there's still a lot more work to be done in terms of fidelity of these models to the prompts themselves. I hope that answers the question.
So yeah, maybe a follow-up question. So you say the attribute binding is solved. Well, just by focusing on the nouns, you can bind the colors to that particular noun. And is this because of the representations that are trained with attention or so, that you have this binding already in the representations? Or do you have another explanation?
It's a very interesting explanation, like a phenomenon that occurs here. And I think what happens is, if you have this issue of neglect and the object doesn't appear in the image, then the attribute doesn't really know where to go, right? But if the object has a strong representation and a strong activation, then it's much easier to connect the attribute to the subject itself. I think that's what's going on here. If the subject doesn't appear anywhere, I'm going to try to put the attribute somewhere, but maybe I'll put it in the wrong place. But if the object has a strong activation, it'll be easier for me to match the color to that object. But it's not perfect, but I think that's what's going on here.
Okay, thank you.
Any other question?
Hi, thank you. This was really exciting work. The artist in me is really excited about the possibilities. I was actually wondering, especially for the personalization and the creativity aspects, how sort of computationally expensive is it to create one of these new tokens? And do you think, is that a limitation of the model? Do you think that's something that needs to be addressed or can be addressed? Or yeah, what are your thoughts on that?
Yeah, so that's a great question. I think there's also many people that are working on this today, this idea of personalization. Textual inversion, we start off with I think it took about 3 hours to train a single concept, which is on a very simple GPU. That's a very long time. People have been able to optimize this to about a couple minutes, depending on the concept, depending on the technique. There's also a growing field that's kind of called encoder-based approaches that try to train a model that, using a single forward pass through the model, is able to give you that representation of the concept, right? So this is giving us into real time, right, where I have an image of my concept and I immediately get my representation and can place the concept into new scenes. But these encoders, it's a bit early on, and there's still more work to be done. There's been huge improvements in them, but this is also an active area of research as well. but we're moving towards more real-time and more scalable approaches. Yeah.
Cool, thank you.
More questions? Well, I have a last question regarding your concept lab work. So during the process of contrastive learning, is it possible to use, instead of the description of the images, another image or visual encoder to do this process? Or, yeah.
So do you refer to the textual constraints instead of, like, say, a photo of a dog or a photo of a cat, use images?
Yeah, exactly. I think could
Yeah.
be probably not that optimal, but
We didn't try it ourselves, but I think because we're talking about the same space in the clip space, I think it could be possible. I don't know what you would get, but I think it would also be very interesting if there's, say, an object that you really can't describe with text, if we're able to use its image in order to guide the negative constraints. But we didn't try this ourselves, but it would be interesting to do so.
okay, thank you. Probably a last question from the audience? No? Okay. Thank you, Yuval. It was very nice, your presentation, and well, I can let's say thank you.
Very much.
How you go? So now we have another coffee break, right? And then we come back to the real last session. Sorry.